Let's look at now the vector equation of a circle as opposed to a line we looked at yesterday. Well, in 2 dimensions, and we saw this with complex numbers, I guess, it's similar to saying, you know, the modulus of z minus z naught is equal to a radius. Well, it's exactly the same thing, isn't it? We're saying vector minus vector naught equal to radius. So that would be the vector equation of a circle in 2 dimensions. The center would be v naught, wherever the position vector ends up on that. Its radius would be r units. Okay, let's just go and show that yes, indeed, this is a circle. So if I break it into its components, then in the I direction I'll have x minus x naught, and y direction, the j direction, y minus y naught. The magnitude of that, so we would end up with x minus x naught squared plus y minus y naught squared is the radius squared. That is, of course, what we recognise to be the Cartesian equation of the circle. Now we know cos squared plus sine squared is equal to 1. Therefore, r squared cos squared plus r squared sine squared must be r squared. And you're going to be, well, why on earth am I doing that? The reason I'm doing that is I can now create parametric equations for these. So x minus x naught, I could substitute r cos theta in, and y minus y naught, I could substitute r sine theta in. And of course I could have done it the other way around if I wanted to, but this creates a pair of parametric equations for the circle in vector format. We're now going to show that this does indeed represent a circle, and we're going to find its center and its radius. So we're finding the dot product of these 2 vectors. Well, in fact, if you look at it, it's dotting itself. Well, if it's dotting itself, magnitude squared. So therefore, it's r minus 2i plus 3j squared is equal to 12. And actually, I now don't have to work out what that is, because I just find the square root of both sides. It's in the format I now recognise to be the equation vector, to be the vector equation of a circle. And I can read off that. So the centre is 2, negative 3, and the radius is 2 root 3. We're going to find the vector equation of the tangent to this circle at the point 3, 4. It's going to look a little bit different to what we saw yesterday as a vector equation. But there's the tangent, it's going off at the point 3, 4. R is some random point on the line, so we're basically saying the vector PR then would be whatever the position vector of R is, minus 3i 4j. We know that the radius is perpendicular to the tangent, so I've just drawn in the position vector OP there. So the dot product of those 2 vectors must be equal to 0. Therefore means that technically is a vector equation for the tangent, because those 2 things dotted together equals 0 is certainly a true statement, and that would represent, because the only variable in there is r, and that's the line we're trying to find the equation for. So that technically is a vector equation, just a different way of writing it. So what would the Cartesian equation of the tangent be? Alright, let's go and actually work out the dot product to come up with the vector equation. So you'll notice I've put in x minus 3i plus y minus 4j for r. There it is. Remember? X minus 3 will be times 3, y minus 4 is times 4, so it's a very simple expansion. Tidying it up, there's the equation. 3x plus 4y minus 25 is 0. Let's push this idea through to 3 dimensions. We now won't have a circle, we're going to have a sphere. But the equation stays the same, because now we're talking 3 dimensions, and we're saying any point in 3 dimensions is the same distance from a centre. Sure, there'll be a whole heap of different circles, but put all those circles together, you've got a sphere. So that's going to be the vector equation of a sphere in 3 dimensions. Centre, v naught, radius, r units. We can find the Cartesian equation of a sphere very easily. Similar to what we did with the circle, we say, well, it's the magnitude of that is equal to r, then there is an equation. That is the Cartesian equation of a sphere, and again it demonstrates this idea of how 2 dimensions flows through the 3 dimensions. We've just added in the z minus z naught squared, so it still has that same setup, like the circle in 2 dimensions becomes the sphere in 3 dimensions. I won't go through and prove this one, but there it is. It's the parametric equation of a sphere. I think it's highly unlikely we'll need to know it. They'll probably give it to us in any question or something like that if we have to use it. But that's what it would look like. You'll notice there's actually two parameters controlling it. So there's theta and there's also phi as well, controlling the different points. So we've been given two spheres and they intersect at a circle. So if you imagine two spheres, or two tennis balls if you like, that might be easier. If you were to slice off part of the tennis balls and put them together, well, where they join would be a circle. So we want to know, what plane does this circle lie on? Because it's going to be some plane in there. If it's a two-dimensional shape that it's intersecting at, you've got to lie on some plane. Well, solve them simultaneously, and fortunately I picked the numbers quite nicely here. Oh look, the x and the y's just cancel straight away, we don't have to do anything. So we get z plus 2 squared minus z minus 4 squared is 9, z equals 7 on 4, and that is the equation of a plane. Remember we said planes parallel to the xy plane will always be z equals some constant number. So z equals 7 on 4 is where this circle lies. Let's find the centre and the radius of that circle. Well, we now know z is 7 on 4, so I just substitute that in and I come back to a two-dimensional shape, a circle whose equation is x plus 2 squared plus y plus 3 squared is 175 on 16. I didn't say the numbers were going to be nice, but here's where we've got to be careful. The big mistake here is writing down the coordinates of the centre. Don't write down minus 2, minus 3. We're in 3 dimensions here. It still has a z value. Yeah, it's 7 on 4 because it's lying on the plane. Z equals 7 on 4. But the actual point that the centre is at is minus 2, minus 3, 7 on 4. And its radius was square root of 175 on 16. Find the intersection points of the sphere and the line. Okay. If we substitute the vector equation of the line in for r, then that's, I guess, solving them simultaneously. Now let's group those components together. So I've got lambda I minus 2j plus 3 minus 2 lambda k. The magnitude of that is 4. Therefore, the magnitude, so lambda squared plus 4, and then we've got a binomial expansion there for the other one, will equal 16. So we've ended up with a quadratic to solve. Again, didn't say the numbers are necessarily going to be nice. So lambda is 6 plus or minus the square root of 51 on 4. So it looks like it intersects at 2 places. Okay, well that makes sense. It's similar to a circle, isn't it? I mean, a line could miss it, touch it, or cut it. Well, it's the same with a sphere in 3 dimensions. You've got a line, it's either going to miss it altogether, touch it, or cut it. This one must cut through the sphere. The fun, of course, comes in the substitution. X will then be 1 plus 6 plus or minus root 51 on 4. Y is nice and easy, it's just 2. Z will be 3 minus 12 plus 2 root 51 on 5. Okay. So there are the 2 points of intersection when I work out what those different x and z values are. Now, this one. Let V be the position vector of a point P on the sphere. The sphere has centre C. So therefore we've got that the complex numbers. The magnitude of V minus C is equal to R, where C is that. Do not prove this. Make sure you read those words. Do not prove this, don't waste time. The equation of the line L through P in the direction of the vector M, W equals V plus lambda M. So that's the equation. Find the values of lambda that correspond to the intersection of the line and the sphere, and your answer is going to be in terms of these 3 vectors, V, C and M. Well, I'm going to need a diagram for this. So there's my sphere. P is just some point on the sphere. Now W is on the line of this vector. So W is the random point on the line. I put it the other point of intersection. I'm assuming it's cutting it twice. We know then that W minus C, the magnitude of that, must equal R, because if W is on the surface of the sphere, it satisfies the equation of the sphere. But we said W has the vector equation of V plus lambda M. So let's substitute that in. Therefore, if I square both sides, but squaring is the same as the dot product of itself, is equal to the radius squared. Expanding that out, I've now got V minus C dot V minus C plus 2 lambda V minus C dot M, and lambda squared M dot M is equal to R squared. V minus C dot V minus C is the magnitude of V minus C squared, and M dot M is the magnitude of M squared. I'm getting closer because I know that the magnitude of V minus C squared is the radius squared. But it equals the radius squared on the other side of the equation, so now the R squareds disappear, and I'm left with something with V, C, and M. There we go. If I solve this, I get two possibilities. So I've factorized out the lambda. So either lambda is equal to 0, or lambda is 2m minus C minus V over the magnitude of M squared. Let's go back to what we were trying to prove here. Find the values of lambda. I've done it. Give your answer in terms of. Well, okay, one of them didn't have any of those in it. It was equal to 0, but the other one is in terms of M, C, and V. Now we're going to deduce that that line is a tangent, so it only touches it in one place. If, and only if, M dot V minus C is equal to 0, and interpret this result geometrically. Well, if it is a tangent, there's only one point of intersection. We know that. So in other words, that random point W that I said was on the line must be at V, because it's the only point of intersection. So V plus lambda M is V. Lambda is equal to 0. Okay, but that means that minus 2m dot C minus V over the magnitude of M squared is equal to 0. Remember, the other option was that lambda equals 0 anyway. So that one's already 0. This one, I have to show, well, that's going to be it as well. So there is, there's the condition. M dot V minus C is equal to 0. You see, the first option wasn't an option, because lambda equals 0. Remember, it could have been anywhere for that one. It must be the other one, because we need both of the answers to come out to be 0. Because if both of those possibilities are 0, then the only possibility is it's a tangent. 2m dot C minus V over magnitude M squared is not 0. Then we have two possibilities for lambda, so there are 2 points of intersection. So as I say, if the dot product equals 0, then the tangent must be perpendicular to the radius. That is the geometric interpretation. So basically we've proven that our result from 2 dimensions, that the tangent is always perpendicular to the radius, holds true in 3 dimensions as well. When we talk about a sphere, the tangent is always perpendicular to the radius. Alright, let's just go outside the syllabus a little bit here, just something interesting. Well, I say outside, I'll mention something in it as well, but other common graphs in 3D. Now the syllabus pretty much says lines, spheres. Okay. There's so much more. A plane, of course, we have seen a plane, but a plane will be anything that's in that format. The power of x is 1, the power of y is 1, the power of z is 1. Now the coefficient might be 0, so it might be just z equals a constant number or something like that, but anything that just has an x, a y and a z equals a number, you're talking about a plane. A hemisphere would look like this. Z equals the square root of r squared minus x squared minus y squared. Now that's a hemisphere that sits on the xy plane, hence why it's minus x squared minus y squared. If it sat on the yz plane, then you'd see minus y squared minus z squared. And so a paraboloid. So a parabola, we know, is y equals x squared, is what we used to see. The paraboloid then is, well, I've done it as z equals x squared, but now we introduce the other variable plus y squared. So that paraboloid would open up in the z direction. So that's where the concavity goes. If I wanted it in the x direction, then it would be x equals y squared plus z squared. A cone in the z direction would have this equation. So some constant number outside of the square root of x squared plus y squared. Again, that's one that opens out into the z direction. Ooh, now we're having fun. Hyperboloids. So this is if you look at the two-dimensional shape, so imagine just doing a cross-section down the coordinate axes or something, you would get what we recognise to be a hyperbola. So it's like rotating it, like we did in, you rotate it around the axis, you get the hyperboloid. This is what was called a hyperboloid of one sheet, because it's all one surface, and it has the equation x squared plus y squared minus z squared equals some number, and minus the z squared, because again it's opening up in the z direction. As opposed to a hyperboloid of two sheets, it's still the same hyperbola, but you see the surface is now going away from the shape instead of inside the shape. And what's the difference? Both y squared and z squared are negative now. It's not just one of them, two of them are negative. So that's what we call a hyperboloid of two sheets, which brings me to the helix, or DNA if you like. There's the parametric equation for a helix. So you see two of them involve the sine and the cosine ratio, and then the other one's usually just something to do with the parameter itself. So t might be a multiple of t, and so 5G, that ends our little look at vectors.